So, what things we have learned yesterday? What things we have learned yesterday? Yes. So, if you remember, we have end to end talked about the complete architecture of how the AlexNet will work. But before that, obviously, we have finished our discussion of how can we, in any of the deep learning pipeline, once we will train the model, how can we save the model so that again and again retraining of that same model should not be required, and then how can we make the model predictions, maybe via loading the saved file or after running the training set, in any of the ways, right? How can we make sure that we will be able to get the appropriate predictions by the model? So all of these things we have covered up in our yesterday's class. After that, once we will be able to build end-to-end pipeline of a very, I would say, simpler, this is one of the simplest project that we have done, where we have seen that how can we use the CNN-based architecture on MNIST-based data with the end-to-end pipeline. Then we started our discussion towards the advanced CNN-based architectures, if you remember. So in the advanced CNN architectures, we have started our discussion towards AlexNet, which is a very, very famous architecture. We have seen its research paper as well. Jeffrey Hinton, again, one of the very famous researchers who helped to build this specific architecture. So what is the beauty about this specific architecture? Anyone remember? What they were doing in the AlexNet, if I will ask you in a simplified manner? Who will explain me? What they were doing in the AlexNet architecture, what we have learned in our yesterday's class, what we have observed in our yesterday's class. Yes, AlexNet is composed of, that's true, they are working on, they have worked on image net based data. Now, ImageNet based data is a very high resolution images will be there inside this specific data set. It means that there will be a RGB channel, means 3 channels will be there. That is for sure. In the ImageNet data, we have seen that there are 1,000 unique classes we have. So it will be able to check that which specific class that specific image belongs to and will be able to give us the answer. What kind of architecture it looks like? Do you remember? How the architecture of AlexNet looks like? How the architecture of AlexNet looks like? CNN to theek hai, I have already mentioned it's advanced in an architecture. When I'm saying how the architecture of AlexNet looks like, very good. So I'm talking about the count of convolutional layers, max pooling layers, all of those things. So if you remember in our yesterday's discussion, let me open a collab file. Just if you will try to remember via the way we have created our layers yesterday, then it will be very helpful for you to give this kind of answers to the interviewers as well. So they can ask you this question that how the AlexNet architecture looks like. If you will be blank or you will say these kind of answers the way you are saying to me, then it indicates that you are not aware about the concept, even though you are aware. So This is not something I really want to open now. Open. I think this was the session file. This was the, I think, yesterday's file that we have worked upon. So here, if I'll go below, I think you can talk about that the architecture is somehow composed of 5 layers that we have covered up in yesterday's session as well. So I hope now you will be able to recall. These are the 5 layers we have, in which we have the first 2 layers, which is composed of a combination of convolution plus max pooling. Plus max pooling. After that, we have 2 layers simply of convolution. Then again, we have a last layer, which is composed of convolution plus max pooling. Yes or no? So in this way, we will be able to see that in AlexNet, we have 5 specific layers. In a broader sense, we are speaking over here. Although if you will try to separate these layers as well, the convolutional and max pooling, then obviously the count will be bigger. But here, just for our understanding per se, just to remember per se, I am giving you a better context that you can answer it, that it composed of 5 layers, where first layer is kind of a combination of convolutional and max pooling. Second layer is again a combination of convolution and max pooling. Then we have layer 3 and layer 4, where just convolution is there. And then at the very end, again, we will be having a convolution and max pooling. Once the specific steps are done, we will be jumping towards the neural network architecture. Yes or no, everyone? In AlexNet, we will be jumping towards the neural network architecture. And this is the same thing which will happen in today's work as well. So in almost all the advanced uh, architectures which you will observe, which are working internally in almost all the business use cases, you will be able to observe similar thing is happening, that we will be having firstly initial convolutional layers, and at the very end we will be having a neural network architecture. So specifically in AlexNet, if you remember, we will be having, again, I think 3 layers we have. So let's try to see and get the understanding of that as well. So we will first of all do the flattening task, so that this specific layer will become the input layer, right? After that, in this specific case, we are working towards 2 hidden layers. 2 hidden layers of having neurons 4096 and the activation function as ReLU. Also, in these architectures, we are using a drop out. So have you guys explored about this? What is the purpose of dropout? I think in the last class also I have told you. The purpose is to reduce the overfitting of any specific model. What is the meaning of overfitting? How many of you know? It's exactly same as what you might have learned in your machine learning classes. So what is the meaning of overfitting? Do you guys remember? Or do you guys are having an awareness? Model performs bad on unseen data, works well training, less in test, high testing error, low training error, dropping few neurons which help model to not overfit, best on training but not on testing, extreme values, high variance, low bias. Yes. So whatever definitions you guys are giving all in other way, I think everyone is actually giving the correct answer. So it's very good to see that people know at least the very much apt concepts of ML. So in deep learning also similar concepts are applicable. That's why I usually say to the people who wants to learn deep learning as well, that first of all, try to have a good understanding of ML concepts. then it will be really helpful for you to get a better understanding of the key terms that we will be learning in the deep learning stuff also. So in Dropout, it reduces the overfitting. The simple meaning is, whenever we will talk about this term of overfitting, that we will be having a low bias and high variance. And this situation is what we call as overfitting. Bias and variance both are the terms used for error. So these both are the errors, I would say. Bias indicates the training error, and variance means that how much your data is varied with respect to the test training result that we will be having. So when you will be having a very high bias and very high variance, it indicates that the overall error of your results is very, very high. So when you say that overfitting is happening, it indicates that at the time of training, the error is very less. So it seems that our model is working really good, and we will be very happy that, hey, we have trained our model on XYZ data set, spent a lot of time, and now we are in a situation where the biasness of the model or the error of the model in terms of training part is very less. But as soon as you will go and check the error for the unseen data or the test data, it abruptly shoots up. So what is happening is, as soon as your model is checking that unseen data, it won't be able to give us the appropriate result. Error is very, very high. So at any point of time, whenever these kind of situations happen, which happens quite a lot, by the way, in the company's work, so at that point of time, we will see that our model is suffering from overfitting. Now, what might be the root cause of overfitting of a model, specifically in deep learning architectures? Anyone, any idea? Anyone having any guesses? So my question is, what might be the possible reasons? What might be the possible reasons of overfitting, specifically in deep learning context? In deep learning context while creating a neural network. Yes. Anyone having any guesses? I'm talking in terms of deep learning concepts, deep learning context, where you are trying to create the uh, neural network, rather than I'm not talking about the ML stuff where we have talked numeric data. Too much training might be a possible reason. What else? Very good. So one answer I am accepting. I got one answer from a few of the people that it might be the case that the user, the developer, is doing too much training. Uh, Maybe they have mentioned the count of the epochs is very, very high. So we will talk about in upcoming sessions that how can we make sure that the epochs value should be optimal. For example, in our implementation also in the last class, if you have observed, we manually have put the value of epoch, which is not usually a good practice. So in real-time projects, this is not recommended actually. For example, here we have put directly the value of epoch as 5, although it's a very, very small value we have put. But usually we don't prefer to put any specific number, hardcore number, or even if we will put, there is a technique which we will cover up later on, which will help us to automatically stop the training at any point of time when your code will realize that overfitting is happening. Do you have an idea what is that technique? If you don't have, it's okay, we'll cover up in the upcoming class. What other issue might be in deep learning context? Too much training I'm accepting. Uh, Very good. So another answer which I'm getting, which is again I'm accepting over here, is insufficient training and testing data. Testing to chalo, let's try to take it separately. Uh, we are talking about overfitting. So what might be the possible reason for the overfitting? It might be the case that your dataset size is very small and model is just memorizing the patterns, and it is memorizing in such a way that if there is a complex in between noisy data point also we have, it is trying to remembering that as well, right? So that might be the reason. Any other reason? So second reason which we can mention is that we will not be having a sufficient training data. So insufficient training data in deep learning might also lead to overfitting. The technique which helps us to avoid this specific situation in deep learning is what we called as data augmentation. How many of you have heard about this term, data augmentation? Have you ever heard of this term? To avoid this problem of insufficient training data, data augmentation, meaning that here what we are doing over here is that whatever data we have, we are trying to do the permutations and combinations of a given data by doing a flipping, rotation, cropping of, I would say, similar original images. So this will help our model to have more training data samples to train. Okay? So this is the practice of data augmentation. So usually you will find that the people who are working in the healthcare domain, I'm taking this example because I personally have while working in the research part at IITH, I was working in healthcare domain, research of AI. So there, I was working with the CT scans of the patients, and the data was very less. This is a very, I would say, bad thing about healthcare domain, that the data set which you will be working with will always be very, very less. The main reason is, let's say if you are working with a cancer based data, the people who are suffering with cancer versus the people who are not suffering with cancer, you can imagine the difference between the population who is suffering from cancer versus not suffering from cancer. This is quite a huge difference, right? So that is where the problem of insufficient training data comes into picture, or imbalancing of data comes into picture. And that is where people try to apply these kind of practice of data augmentation. So in future, whenever someone will say that, hey, I have applied data augmentation in my training part, so you should be able to understand that what they clearly want to signify you, that in a way in their project they're suffering from a problem of insufficient training data. So what they have done is, whatever be the original images they have tried to do the flipping, rotation, cropping of those similar images and create multiple sub images of the main image, and they try to train those specific images as well in their training set to avoid the issue of overfitting. I hope you're getting my point. Shall we move ahead? What could be the next, maybe the cause of overfitting in deep learning? As I already have said, noisy or irrelevant data. Noisy or irrelevant data. So it might be the case that whatever data you are working with, that is not a relevant data itself. Or if it is, it contains too much noise. What is the meaning of noise? The data set which you are working with to train the model, this is not an apt data. It contains too many wrong entries, right? Or the images are not that much clear. It is noisy. So at that point of time, if your data is not of quality manner, so how can you expect the predictions will be apt? So that is again another important thing. too much training, I was talking about this part as well, that usually people don't write. That is why the epoch entry. And even if they write, there is a concept of early stopping in deep learning. I'm writing all these concepts in green, uh, if you will say green point. The main reason is if after the session will get over, I will share these notes with you all. And whatever the techniques I'm talking about in deep learning, today, your task is to explore more on top of this. In the upcoming session, all of these techniques which I'm writing in the green pen, we will try to implement it in our collab as well while doing a project end to end. But these are the very famous techniques which people usually use in deep learning to avoid this kind of situations. So in early stopping, what usually do, it simply, I would say, stops the training. It simply stops the training at any point of time when it sees that the validation set performance, validation set or training set, I would say, performance stops improving. ठीक है? So that is the main purpose of early stopping. So I hope you all have seen in our starting of the mini project that we usually get the validation loss, right? In every iteration, and the validation accuracy in every iteration. So when we apply a technique called as early stopping, it will check very closely that whether the accuracy in every epoch is increasing and the loss in every epoch is decreasing. If at any point of time our model will observe that after some epochs the validation accuracy is not increasing or the validation loss is not decreasing, it will automatically stop at that point of time. So that is what the technique is, we called as early stopping. So automatically it will stop earlier. That's the whole point. So is these 3 points are clear to everyone? Before we will move ahead. Imbalanced data comes under this insufficient training data point. So I have already covered up. Uh, Next important reason might be for the overfitting is the lack of regularization. Lack of regularization. I think in your machine learning, you must have understood about the concept of regularization. So regularization is a practice which is basically used to, I would say, handle the overfitting in the training set, in the training data. So I'm pretty sure that in terms of ML-based algorithms, you must have learned about L1 and L2 regularization method, which we also called as lasso and ridge regularization techniques, right? Have you guys ever heard of these techniques? Yes, there was one question. Let me take it up. If epochs are 10 and after 5 it sees that nothing changes, then it would stop at 5. That's called early stopping, right, ma'am? Yes, that's absolutely correct. So in the early stopping, as I have explained as well, and whatever you mentioned is correct. So let me explain you by a graph as well. So if let's say this is the epochs, and let's say you have mentioned that my epochs are 100. As of now, what we are mentioning is a strict number. But let's say when you are saying epoch says 100, and you will mention that early stopping technique should be applied. How will we mention that? We will mention in that same line when we are trying to do the training part. But I'll showcase you that implementation. That is a separate story altogether, which is quite easy. But for the understanding per se, you will be able to observe that in the y-axis, we are having the performance. Now, when I'm saying performance, I'm including both of the things, accuracy and the loss. So for now, let's observe, let me take it as a performance in the form of a I would say loss factor. So you all know that as the epochs will increase, the loss value should be decreasing, 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 decreasing. Now, let's say this is the epoch number 50. at epoch equal to 50, your model will be having a minimum loss. And as soon as you are doing a further training, the loss somehow starts stagnant and then shooting up, right? 51 पे यहाँ है, 52 पे यहाँ है, 52 पे, 53 पे यहाँ है. So as you are increasing the epochs now, what is happening is, and it usually happens. So if you are saying 100 strictly, so it might be the case that at the 100 point, your loss might be at this point. But we all know that this is the minimum point where the loss is minimum. When I'm saying loss is minimum, accuracy is maximum. Yes or no, everyone? So this is the point where I'm saying that the accuracy is maximum and the loss is minimum. So when we apply early stopping, by the name itself, it suggests that the total epochs mentioned was 100, but I'm stopping early. I'm stopping early my training process because I got the minima as such in terms of training process. ठीक है? So this is what we call as early stopping. So lack of regularization is another thing which we were discussing. Now, in terms of machine learning part, regularization technique is what we have as dropout, which we are covering up. Few minutes back, I have talked about. So what it usually does, or you will see that this dropout is something which you will see almost all the advanced CNN based architectures, they are using it. What is the meaning of dropout? Dropout itself suggests that it will try to do the dropping of the layers which you are connecting, fully connected layers. So maybe few layers will be dropout. Dropout meaning that the randomly our model will deactivate. Randomly our model will deactivate the neurons during, I would say, training. So whatsoever neuron is having a very slow training, very slow learning, or maybe there are few neurons available in the layer which are not even participating in terms of learning, in terms of grabbing the features. So automatically in the dropout, it will try to remove those specific layers or the neurons, not layers, neurons, in terms of doing a participation, and it prevents the co-adaptation. I hope it is clear to everyone. Apart from this, any other cause? There are other causes as well of overfitting. Maybe you have not done a proper hyperparameter tuning. So there is a very poor hyperparameter tuning which you have done in your project, and that might be the reason or the cause of overfitting. So it might be the case that, for example, in deep learning, we will be having learning rate as the parameter. We will be having batch size as the parameter. And you are just taking these numbers randomly. You have not done an appropriate research with respect to the data set that you are working with, whether it's correct or not. And that might also lead to, I would say, overfitting part. So these are the few, I would say, reasons in deep learning context, which are the possible ones because of which the overfitting is happening, right? Suppose a neuron contains important information, it will get dropped. Will it impact the model? So if any neuron contains important information, so it will never ever get dropped by the model. Every specific neuron is having the weights available with them. And when the weights are good and high, it means that that specific neuron contains important information. So that specific neurons will not be dropped out. Dropping out means that the neurons which contains lesser information or no information at all. So that is where our model will do the smart job and will remove them so that they will not even participate in the training part itself. And our training will also be done very much faster manner, and overfitting will not happen. Is this clear? Shall we move ahead now? So that is the overall discussion in detail that we have done about AlexNet. Today, we will try to see more on top of this, and we will try to talk about a very interesting architecture called as VGG16. Again, This specific architecture also tries to work upon the ImageNet based data. Again, the same data which contains 1,000 classes at the very end. So you will be able to observe that in this specific architecture also, we will be having at the very end softmax activation function, which helps our model to decide that which specific class it finally belongs to. But the internal architecture of VGG16 is quite different from what we have in AlexNet. And people usually prefer to use this specific architecture as comparable to the previous one. The only reason is that this is, I would say, quite a simpler architecture as comparable to the above one in terms of remembering as well that how much is the filter size, stride value, and the max pooling layers we have. So let me try to work upon it and we'll try to take the image of this specific architecture of VGG 16. I hope the screen is architecture is properly visible to everyone. It will drop randomly whenever we rerun our model. It will affect the accuracy of the model. Uh, Saurabh, yes, just that's true. Maybe when, so whatever words I have talked about in the above part, just I have showcased you the internal intuition behind early stopping, data augmentation, dropout, everything. Try to grab as per the conceptual part. Uh, in detail, in terms of doing the implementation, we will do it in the upcoming session. So don't worry if you don't get it 100%. Even I have not explained it 100%. I have just touched upon these concepts so that you should know and have an awareness about this. Is this clear? Shall we move ahead? Now, this is the very interesting architecture that we have in VGG16. I'm trying to get the research paper. So this is the research paper, which you will be able to see at your end as well of VGG16. So VGG 16 is nothing but very deep convolutional networks for large scale image recognition. Again, at your end, once the today's session will get over, try to read this specific research paper in a lot more detail. But again, you can easily able to see over here that we investigate the effect of convolutional network depth on its accuracy in the large scale image recognition setting. Main contribution is a thorough evaluation of networks of increasing the depth using an architecture with a very small convolutional filters. So one interesting thing is that if you will be able to observe in AlexNet that we have covered up yesterday, it was quite confusing, right? Sometimes in that specific architecture, they were using the kernel size as 11 cross 11. Sometimes they were using, I think, 5 cross 5. Sometimes they were using 3 cross 3. So it's hard to remember as a person who is working in this specific domain with the exact values, right? And that's why in the yesterday's class also I told you that don't cram these values because no one, even I don't remember these things at the time of doing the implementation. The more I use, automatically my brain will be able to recall. But if let's say for a few months I won't use that specific architecture, I will also forget that. But the beauty about VGG16 architecture is that it works with a simple 3 cross 3 convolutional filters. Now what this specific architecture says, if you will be able to see, This architecture is composed of simply convolutional, ReLU is the activation function, and max pooling. So in the initial steps, you will see that they are using convolution, max pooling, convolution, max pooling, and they have predefined that, hey, when I will be using the convolutional layer in my architecture, when I will be using the convolutional layer in my architecture, so at that point of time, my filter size will be 3 cross 3. The stride value will be equal to 1 and the padding will be same. How many of you know the meaning of this thing? Padding will be equal to same. Yep. I think in the yesterday's class, I have covered up this specific concept. Padding equal to same is a very generic concept in deep learning, which says that I don't care that whether you want to apply a padding as 1, 2, 3, 4. I don't want to work upon the numbers. I will just make sure, as in when you're saying same, I will just make sure that the input and output image dimensions are same. Now, how will it be same? How the padding will be applied? I think in a very starting of the discussions we have covered up. So I am assuming that you all know, right? How it will make sure that the dimensions will be same. So this is about a convolutional layer which is applied in the VGG16 architecture. Then we have a second layer which we have seen few minutes back. The layer was max pooling layer. The purpose of max pooling layer, I hope again everyone knows, is to reduce the dimensions so that overall the computational complexity will be bit less. Now in max pooling layer, it just makes sure that we will go with the filter size of 2 cross 2 and the stride value as 2. So basically what it does in both the layers is this specific architecture, I would say, standardize the values which helps the people like us to understand and to use it more frequently, because this kind of standardization, if you have ever observed in the yesterday's session, was missing in the AlexNet architecture, right? Even though this VGG16 have a why it is called 16, because it contains 16 layers. Nowadays we also have VGG19, right? Sometimes 19 wala is better, sometimes 16 wala is better. The only difference is that contains 19 layers and it contains 16 layers, but the architecture internal working intuition will be exactly same, right? Now shall we move deep dive into it and we'll try to understand that what this architecture is doing? So again, we are providing the image. This image is from ImageNet data itself, which contains high resolution images, RGB images, size, if you remember, 224 cross 224 cross 3, where 3 indicates the RGB channels. So you can see the background image, it's a colored image, right? I think it's an image of a car, if I'm not wrong. But anyhow, they are directly feeding this specific image in the VGGNet architecture. Is that clear? Now, what they are doing is they are trying to take two convolutional layers, which you can see. So this black black one indicates a convolution layer, and this red one in the image indicates a max pooling layer. So when we are trying to feed the 224 cross 224 cross 3 is the RGB channel to the convolutional layer, considering that this is having the 64 filters available with them, and after that we're directly feeding them into a max pooling layer, right? So how much is the size of your dimensions? How much is the size of your dimensions? Now, always make sure when you're moving ahead from left extreme to the right extreme, in this specific case, the convolutional layer, take it as a fixed size 3 cross 3, stride is 1. And as and when you're encountering the max pooling layer, take the fixed size of filter as 2 cross 2 and stride as 2 while doing the evaluation. And what specific formula you have to apply to get the output dimensions? It will be same as n minus f plus 2p divided by s. If you will be having a decimal value, you have to convert it into lower bound plus 1. Same thing you have to apply. So if I will go back to our research paper, do they have the architecture available in the research paper? They should have. Okay, they have not mentioned the architecture. It's okay. Let me try to grab this image. क्या हो गया? So in terms of understanding per se, you can take it very easy. What is happening in VGG16? We are providing an input image. See this specific graph very easily. We will be having two convolutional layers, then pooling. Then again two convolutional layers, then pooling. Then we have three convolutional layers, then pooling, three convolutional layers, then pooling, three convolutional layers, then pooling. So for the first two layers, if you will be able to understand, what we are doing over here is we have two times a convolutional part followed by one time the max pooling part. ठीक है? And for the upcoming three layers that we have three times convolutional part and one time max pooling part as the step number one. And the step number two, you all know, we have to work around towards creating a neural network. Is this clear? Comfortable till so far? Can I get the confirmation over here? Now, If it is clear, then we can work around with the numbers, how we are getting these numbers. Maybe you guys can let me know how we are getting the dimension as 224 comma 224 comma 64. Let me know. 64 is the kernel size. Okay. 224 cross 224 is the shape. Then how it comes as 112 cross 112 cross 128? Max pooling, very good. So when you are doing a max pooling, what will happen? Again, apply the formula. N is 224 minus filter size. What is the filter size in max pooling? It's fixed 2 cross 2. Do we have a padding? No padding. Do we have a padding? No, we don't have any padding in the max pooling layer. Padding will be same in case of convolutional layer, not in the max pooling layer. That is why if you will be able to observe in the convolutional layer, the input image size which we are passing and the output image that we are getting is exactly same. I hope you're getting my point. Now, as in when you're applying a max pooling, so it will be no padding. Stride, how much is the stride value? How much is this? Very good. 2 plus 1. So what is the answer? It will be triple 2 divided by 2 is triple 1 plus 1, which will be 112. Is this correct? Is this 112 is correct or incorrect? So here we will be able to get the answer as 112 cross 112 cross 128. How we are getting 128? We have the count of the filters now as 128. Okay. Now again, we are applying the convolutional padding will be there. So it will make sure that the size of the input image will remain the same till the last convolution, which is 112 cross 112. Now again, the max pooling layer will work. We have increased the filters from 128 to 256. So if you will be able to observe, we are starting with 64. And in every max pooling part, we are trying to update the count of filter into 2, into 2, into 2, right? So the next stage we have converted to 128. Now it will be 256. How we are getting 56 in max pooling? Same maths you have to apply. Just apply 2 cross 2 as the filter size and the stride value as 2. So we will be having 112 as the input image minus f is 2, no padding, stride is 2 plus 1. So it will be 110 divided by 2 is 55, 55 plus 1 is 56. So we're getting 56 cross 256. Then again, 3 times convolutional will happen. So we reach to the layer number 3 where 3 times convolution will happen. Because the padding will be same, so the output dimensions will be same only, which is 56 cross 256. Now again, a max pooling will happen. So in the max pooling again, you will be able to observe at every point of time when you apply this kind of a math, which is n minus f plus 2p divided by 2 plus 1, you will be able to observe because we will be having a filter size as 2 cross 2 and the stride value as 2. it will just try to divide the input dimensions by 2. So in a way, we will be able to get here 28 cross 28 cross 512. But if you want, you can evaluate as well. So input image was 56 minus 2f minus f divided by 2 plus 1. So again, it will be 54. 54 by 2 is 27. 27 plus 1 is 28. That's why we're getting 28 cross 512. Again, 3 times convolutional, but it will make sure the input image size will remain the same. So it will be 28 cross 512 only. Then again, max pooling will happen. We will be able to get the dimensions as 14 cross 512. 3 times convolution. Again, max pooling will happen. It will be 7 cross 512. And now this is the stage where neural network architecture will be created. Before this stage, can I get the confirmation that is this clear, whatever we have done? Any doubt in any of the layer? So what I'm trying to ask you over here is this, I will call it as a split of, I think we can split it as layer 1, L1, layer 2, L2, layer 3, L3, layer 4, L4, layer 5, L5. Is this 5 layers are clear before we will reach the last neural network layer of L6 where we will be having a dense, fully connected layers? How 64 will become 128 after doing a max pooling? Because we are increasing the count of the number of filters. So at the very end, this 64, 128, 256, 512 indicates the count of filters. So filter size will be fixed, but we're increasing in every layer the count of the filters, because in every layer we are deep diving into the architecture part. It's an in-depth architecture containing so many layers, and that's the main reason to grab the important features in a lot more detailing manner. In every max pooling, the dimensions will get decreased, but filter count will be increased. So that is what we are doing. That's the whole idea. Shivam. That's what the researchers have done. How it is better than AlexNet, we will come to that point. First of all, you should know the internal working of how VGG16 is working. Then only I can answer this question, right? It's not completed yet. So first of all, get the understanding of this architecture. Then at the very end of this today's discussion, that is the topic, that how it is better than the previous one. Is this clear till so far? Shall we move to the last layer stage of our VGG architecture, where we will talk about what dense layer is doing over here? Okay. So now, if you will try to evaluate this at the very end dimensions in the max pooling, it is 7 cross 7 cross 512. So if you will try to multiply these numbers and flatten this layer, so what is the count of number of neurons? Multiply this value, 7 sevens are 49 into 512. So I think this value will come out to be 4096. Just check it out. Just check it out at your end. So what we have to do is, what was the last value? It is 25088. Let me check. What is the value we are getting? 25. So in the layer 5, we are getting the answer as 25088. Okay. So this is the input value, right? This is the input value that we are getting. It's correct. We are passing this input value now to the kind of an input layer will be having these many neurons, which is 25088. Now these input layer values will be passed to the hidden layer. So when we're saying 4096, it's a part of a hidden layer. So hidden layer contains how many number of neurons? In the next layer, we will be having 4096 number of neurons. Clear? This is correct, right? Now, how many number of hidden layers we have in this specific architecture? How many number of neurons we have, number of hidden layers we have? So we have the dense layer 1, dense layer 2, dense layer 3. So it means that input layer will be passed to a hidden layer having 4096 number of neurons. Further, again, it will pass to further, I think, 4096 number of neurons. So two hidden layers will be there. Hidden layer 1 and hidden layer 2. And at the very end, we will be having a output layer. In the output layer, how many number of neurons we have? In the output layer, how many number of neurons we have? When we will reach to the last dense layer, output layer, it will be equal to, very good, 1000. Why 1000? Because we will be having 1000 classes available in ImageNet classification task. ImageNet classification task. Correct, everyone? Comfortable? Now help me to understand that whether you got each and everything over here or not in the entire architecture. Any confusion, any doubt you have, please ask from me before we will proceed ahead to implement the same in our implementation part. Yes, can I get the confirmation? Explain once more. Then it will take another 1 hour to me. Can you tell me what specific point is not clear? Then if I have to explain again, I can explain, then maybe implementation we have to do in the next class. Because I have taken almost 1 hour to explain this architecture. Input value wala part, it's quite simple. So if you will be able to observe, at the very end, how many number of, if you will carefully see this architecture, in the max pooling layer, where you end your story, you will be having 7 cross 7 cross 512. Yes or no? 7 cross 7 is the input size of an image. 512 is the count of number of neurons. Now, after this specific layer, what will usually happen? This is same as what we have covered up in AlexNet as well. We will apply a flattening layer. Even in the MNS data, similar concept we have covered up. When we are saying flattening layer, what it will do is, it will take the dimensions from the image that we will be having, 7 cross 7 cross 512, and will convert them to the flattening part. Flattening means that one dimension, so you will be able to see this kind of internal architecture, where the count of number of neurons. So this is the very first layer we will be having. And this is the very first layer called as input layer, where our model will feed the input values. So my question is, how many number of input values it will feed, how many number of neurons it will feed in the input layer. So just multiply these numbers, 7 into 7 into 512. So we got the answer as, what was the answer again? Forget. 25088. So it means that starting from 1 2, 3, 4 till the point of 25088. So we are feeding these many number of neurons in the input layer of VGGNet. Now, after this layer, what we are applying is we are applying a dense layer where every specific input neuron will be passed to a hidden layer. Yes or no? To a hidden layer. Hidden layer 1, which contains how many number of neurons? As per their architecture, it contains 4096 number of neurons. 1, 2, 3, 4 till 4096. So every specific, it's a dense layer architecture, means fully connected architecture. Every specific neuron available in the input layer is fully connected with all the neurons that we will be having in the input layer neuron. So this is how the connection will be built. I hope you're getting my point. Then we will be having, this is hidden layer 1, H1. Another hidden layer of again 4096 neurons, fully connected. So again, all the information will be transferred to all the neurons. At the very end, we will be having an output layer of 1000 number of neurons available. 1, 2, 3 till 1000. This is the output layer. Why 1000? This number is something which will be fixed, which you can't change. In between hidden layer numbers, obviously you can change depending upon the hyperparameter values. So it usually tries to capture, if let's say we will be having 25088, this is a quite huge number. So we will always make sure that in the hidden layer, the number of neurons should be less than this specific number, right? Why is that so? Because you know that the weights, if the hidden neurons will also be, neurons will be very high, the weights or the parameters will also be very high. So the computational time to get these optimal values of weights will be very very huge. So this is very very important that you will decrease the hidden layer number of neurons comparative to the input layer neurons, and then output layer numbers will be fixed because it depends on how many number of classes you are working with. So here we are working with 1000 unique classes, so we will be having 1000 neurons, that is fixed number, and then softmax will give the probability of each and every neuron working over here, and whichever is having a maximum probability, that specific class will be assigned. Clear hai? Is this clear to everyone who asked this question? To repeat, can I get the confirmation? Input value, what is that? How it comes as 25088? This count of neurons in the hidden layer, this number is uh, a very informative factor. As I told you, if you will take this hidden number of neurons as very huge number in terms of the number of neurons I am talking over here, so the impact will be what I told you. What will happen if we will take, let's say, in the hidden neurons itself, 4096 number of neurons, sorry, 25088 number of neurons. In that case, what will happen? The training time will be huge. Yes, everyone? The training time will be huge. Also, what we can say is that the compute, it will become a very huge, computationally expensive task. But what if I'll take, let's say, very small number of neurons, maybe I'll just take 20, 30 number of neurons. I'll not take 4096. So what I'm saying is, what will happen if the count of number of neurons will be very less in the hidden layer? What will be the impact? This can be asked from you in an interview as well. So what will you answer? Very good. So there are few people who are suggesting me a very good answer. This is the case where again overfitting might can happen. Can I say everyone? Why I'm saying overfitting? Because if you're using a very lesser number of neurons in the hidden layer, it will memorize the training data, right, instead of generalizing well. So that is where you will always have to make sure that the count of number of neurons in the hidden layer part should not be very huge and should not be very less. It will always be in a balanced manner. समझ में आया? Is that okay with everyone? Shall we move ahead? Shall we move ahead? Okay, perfect. Now, are we ready to implement the same? See, if you have not clear with the internal intuition, then implementation doesn't make sense to you. If it is not clear, I am again and again asking to you. That's what I can do from my end. If it is clear, give me the confirmation so that it will take a lot of time to implement as well. So let's try to start the implementation so that we can finish our session on time as well. Because again, today also I have a lot of meetings end to end. Perfect. Let me try to work on the same file that we were working with. And let's try to implement our another interesting architecture, which is VGG16 architecture implementation from scratch. Also, as of now, I am doing all the implementations from scratch. Today, if time permits to me, I will tell you that nowadays in industries, ठीक है, for understanding per se, we are doing the implementation from scratch. But in industries, we don't do this kind of implementations from scratch. So how usually people directly call these models, and internally this architecture will be working on, and we will be able to get the results directly. So in terms of doing the or writing the code in the companies, it is a very easier task nowadays. I will try to showcase you that as well. But considering that you are doing all of these things for the very first time, so I am writing the code from scratch, but nowadays people don't usually write the code from scratch. They directly call these architectures, and whatever be the things that we are writing, it's already written in the documentation, and directly it will fetch the weights, and they will start working on predicting the part. Uh, I hope you all remember that in our previous discussion, we have seen that we can store these weights in the H5 file, right? So similar thing is happening in the all the, I would say, advanced models which we will be having. So we already have those models saved in open source repository. So people directly fetch those weights and do the prediction rather than creating their own architectures from scratch. That's the whole point I want to convey over here, right? But anyhow, for now, just let's get started with our model. So I think we can first of all import everything, because otherwise we need to start our collab file from the scratch if we will not import it, because we have already done the import part in the previous stage, but I don't want to start from scratch. So let's try to do step one, where we will try to import all the required libraries. So what we can do is import TensorFlow as alias name STF. Then we can from import TensorFlow dot keras dot models. We can import a model name called as sequential, because again, this is a sequential stack of layers that we are working on today. Then what we will import is TensorFlow dot keras dot layers. We will try to import convolutional 2D layer. We will try to import max pooling 2D layer. We will try to import a flattening layer to do the flattening part at the very ending of the stage. We will import dense layer to create the hidden and the output layer. We will do the dropout to do the dropping part. Then we will try to import the optimizer, TensorFlow dot keras dot optimizers will import ADAM optimizer. In the next class, which we have tomorrow, we will cover up about this optimizers also in detail. So just make sure that you will join the tomorrow's session. Okay? Now we will try to call a function, define a function called as build VGG16. Okay? And inside this, we can pass the input shape that our researchers have used in their research paper, which is 224, 224, 3. That's what they have used. And the number of classes which they have mentioned on the dataset is 1000. Now we have to define the function. So shall we start building our architecture? Is everyone ready? So model is sequential. So let's define that first of all. And then now we will work on adding the layer by layer thing that we have covered up. So first layer is composed of, let me check. I think we have written it somewhere. 2 convolutional and 1 max pooling. So this is what I'm calling it as a layer number 1, where I will work on 2 convolution plus 1 max pooling. Comfortable? Then I will write it down first and then we can start working on writing the code. What was layer 2 in our image? Let's check it again. 3 convolution, 2 convolution. Acha, layer 1 is L1 is 2 convolution, 1 max pooling. L2 is also same. So we have 2 convolution and 1 max pooling. Just confirm to me if anywhere I'll write something wrong by mistake. I'm also making sure that everything I'll write is correct. Layer 3, what is that? L3? 3 convolution and 1 max pool. Let me write it down. So that then after that, it's just we have to implement the things without any confusion. 1 max pooling. What is there in layer number 4? Anyone can just give me the confirmation. L4. Is it same? Oh, it's same. I think 3 convolution plus 1 max pooling. Layer 5. Layer 5, what is that? 3 convolution, 1 max pooling. Okay. Quite easy, right? It's so easy. 1 max pooling. So I think in first 2 layers, we have 2 convolution and 1 max pooling. And remaining 3 layers, we have 3 convolution and 1 max pooling. What's afterwards we have? The code to write a neural network architecture, which we will see later on, right? Where we will be having 3 dense layers. We will do it after doing a flattening part. So shall we start writing a code? Everyone is ready? We will do that neural network architecture later on, but first of all, let me have layers itself. We have not writing any code till so far. So shall we start? Okay. In layer 1, how many number of filters count we have? Do you remember? It's quite easy now to write model.add. We just have to add at every point of time. Convolutional 2D. Tell me the filter count. How many number of filters we have? 64. What is the size of the filters? In convolution, filter size is fixed, 3 cross 3. Do we have a padding? In convolution, we always have a padding, which is same. Activation function, ReLU, and it's a very first layer. So we have to pass the shape of input, which we already have defined in the parameters with the same variable. I think we are good to go. If you guys will allow me. Everything is fine, right? Shall we add the second convolution layer? Model.add convolution 2D. The count of filters will remain same. Count of filters will get changed after max pooling, always remember. Filter size will remain same. Padding will remain same. Activation function will remain same. Oh, do we have to use input shape in the second convolution layer parameter? No, not required. What's next is the last max pooling layer. So just call the function max pool 2D. What we supposed to write over here? What is the pool size? Do you remember? What was the filter size in this max pooling is 2, 2. And do we have a stride value? In this case, it is 2, 2. Done. How easy it is, right? Now, let me try to copy this in the layer number 2 and we'll do changes over here. 2 convolution, obviously, so 2 times we have to add the convolution layer. Now, max pooling. After max pooling, are we changing the number of filters count? Yes, we are just multiplying it. So it will be 128. Are we changing the filter dimensions? No. Padding, are we doing? In every convolution, we are doing it? Same. Activation function, relu. In the max pooling, are we doing any changes? No. Quite simple, right? Let's copy this entirely and go to layer number 3. Now in layer number 3, the interesting thing is we have 3 convolutions. I'm just copying one more time. Are we changing the count of number of filters? After max pooling, the count will get changed to 256. Change this in all the convolutions in one go so that we will not forget. Are we changing the filter size? Are we doing padding? Yes, activation will remain same. Any change in max pooling 2D? No, filter size and stride will remain same. Just copy the entire thing in the next layer because we will be having 3 convolution there as well. Yes. Are we changing the count of filters? What is that count? 512, I think. Now, till 512, we are doing a changes, and after that, we're just posing it. So always remember, everything will remain same. And after that, again, when we are jumping, we are not going beyond 512 in the architecture. So now I think this will remain exactly same as the above. We are not doing any change. So are we ready for the next part? So what we have done till layer number 5. So if you will be able to observe in layer number 4 and layer number 5, 512 is the count of number of neurons. We are not going beyond that. Always remember that. Are we ready to create our last step number 2, neural network architecture, where first of all we have to do flattening and then we need to create 2 hidden layers? Or any confusion till so far? Anyone? Quite easy, right? Once we understand the internal working of any architecture, how easy it is to write a code. Now, I think you should feel this thing. If I will start with the implementation and write these bigger lines of code, you will be worried that this is how deep learning codes look like. And that is what actually creates a fear in the head of so many learners, so many people. But once you start learning about the maths and the understanding of the architectures, then if you will write the code, you will find the coding very interesting and very easy. Yes, obviously we have to do a flattening now. Without flattening, how we can create an architecture of neural network? So we need to add a flattening layer. Let's do it. First of all, flatten it. So this will become my input layer now. What else? We need to create a hidden layer. Oh, model.add dense. How many number of hidden neurons they are using? 4096. What is the activation function they are using? Relu. Again, dropout also they are using just to make sure that there will be no overfitting problem. Again, they will be having a hidden layer, dense 4096, activation as ReLU. Again, I have made one mistake. I will quickly. Oh, what happened? क्या हो रहा है? ठीक है? What else? At the very end, output layer, model.add dense. Output number of neurons is nothing but the number of classes that we will be having 1000, which we have defined in the function itself. Activation function will get changed from ReLU to softmax. Reason I think everyone knows. Then I'll return the model. I think that we are doing it correctly, but still if we have anything wrong, we can later on check it out. But let's try to run this. Once you will call this model, then you will get to know that is there anything wrong or not. So you can call VGG16 model, which will be the function name is build VGG16. So let's call this. Let's see. It means there is no mistake in our code. Now, what we're supposed to do is we need to compile it. Let's see in compilation, are we getting any error? So we will use the, again, optimizer as Adam. I think previously also we have used Adam only, right? So everything will remain same actually. Okay? I have just copied it from above. After that, vgg dot underscore 16 dot summary. In one go, we will be able to create our entire VGG16 architecture. It is exactly same as what you have seen in your image. So we have created our own VGG16 architecture. Is it clear? We don't need to mention the input shape, Atul. As soon as you will do the flattening, so automatically, whatever be the last layer we have, which is 7 cross 7 cross 512, internally it will do the calculation as soon as you will do the flattening, and will, whatever be the number you're getting, which is, I think it was approximate 25088, that will become the count of the neurons of the input layer. So input layer will automatically will have 25088 number of neurons. So you don't supposed to write anything as a manual thing over here. ठीक है? समझ में आया? Quite interesting. Quite easy. How many of you feel it's difficult? These are the, by the way, advanced algorithms that we have in deep learning, which we are learning from last class itself. How many of you feel it's difficult? Oh, thanks for letting me know. It is 4096. Now it is correct. Still again, I'll share this file with everyone. Recheck the values. It should be exactly same as what they have mentioned in the research paper on the architecture. If anything I have written by mistake wrong, you can just rectify that specific number. AlexNet versus VGGNet, we will come. Today, wrapping up on that specific topic itself. Don't be in a hurry. Shall we move ahead? Now, usually, as I told you, people don't write the code from scratch. So as soon as they want to use VGG16 model code, maybe let me try to check if I'll be able to get directly any specific website to showcase you. Let's go to authentic website of Keras. So you can see this is the code actually. What we have covered up or what I have showcased you is from scratch. But nowadays, people don't write code from scratch. The very first reason is everyone is not comfortable in writing the code in a faster manner, just like the way we usually do. It's because we do have a lot of practice and experience. That is why it doesn't take a lot of time and effort to write the code from scratch. But considering the people who are not that much good with programming, plus considering the time required to write the code, what developers have done nowadays is they already have made a functions of VGG16, VGG19, whatever model you want to call, right? VGG19 is there. So these are the arguments that we will be having. Include underscore top true weights ImageNet. So weights equal to ImageNet is very important to write because it will try to fetch the model weights directly. No need to do any sort of training to write the code from scratch. This will pick the architecture from what you have done from last 1 hour to write a code. It will directly fetch up that specific architecture if you will just write this parameter as weights equals to ImageNet. Then we have by default this parameters input tensor, input shape, pooling, classes is again, it will be fixed 1000. Classifier activation will always be fixed softmax. What is the name of the model you are using? It is also a very important parameter that I am using currently VGG16 as a model. If you want to use VGG19, you have to mention over here VGG19. Now, each and every argument, what that indicate, include underscore top indicates that whether you want to include the 3 fully connected layers at the top of the network. So if you remember, we have seen that in our neural network, after the CNN portion will get over, we will be having 3 dense layers. So do you want to include that, or if you don't want to include that, that is also possible. So in few of the tasks, if let's say someone just wants to cover up till the very first step and they don't want the second step, maybe they want to apply their own number of hidden layers in the neurons. So that is also an optional thing. So they have mentioned that as a parameter. Weights, ImageNet, we want pre-trained weights, as I told you. Input tensor is an optional field, which is basically used as the image input for the model. If you are working on your own data set in which you will be having your own input shape or input tensor, then you can apply it. Pooling is again an optional thing. Classes will always be fixed. If you're working with ImageNet data, classifier will always be fixed. Name of the model will always be fixed. So what actually we can do to implement the same thing? So let me try to just copy the entire thing and will showcase you the implementation again, but now in a way how industry code works. Okay? So I will again try to use the function name def build VGG16, let's say model, and here I will define the code. The code is the base model, which I will define, is equal to, I'll copy the entire thing that I have taken to make it in a much better manner. I can do one more thing. I can simply import the from TensorFlow dot keras dot applications from where this VGG16 is coming up. You can see in my code. I will directly import this model VGG16 so that in my code, I don't need to write a bigger line. I will directly mention over here the model name and it will be able to work well. So now what I will do, I will have taken this thing. I just remove whatever values I don't require or the optional things. Weights ImageNet I'm using. Input shape is something which I'm using as 224 comma 224 comma 3. I don't have my own input images, so I'm removing this. uh, I think remaining things will remain same. I will simply return the base underscore model. Now, once you will do it, let's say you want to work. First of all, let me try to showcase you working perfectly fine, right? VGG 16 model is equal to, I will call this function. So you can see it is downloading the data from a website, and you can observe over here it's a .h5 file. Can you see? It's a .h5 file. Do you remember what is this extension says? In the yesterday's class, we have seen that we can save our models so that we don't need to retrain our model again and again in the H5 file. Today, we are seeing over here that how the researchers have done the similar job, so that we don't need to retrain our VGG16 model on top of ImageNet again and again. They have already saved their weights, pre-trained weights in the H5 file. And what I have done is I have simply downloaded these parameters to do my work, right? So if I just have to check the summary now of this specific model, you can see this is exactly what we have covered up above. Now, this is one code we have, and this is another code that we have written. Actually, these two codes are doing the same task. But the time required to write this specific code versus the time required to write this specific code, you can imagine the difference. And that's the main reason. Usually, the best practice to follow when you're working in the companies is directly go to the documentation, check which specific model you want to use, and you can directly take the parameters from there and you can work on it. You can see efficient net, ResNet, mobile net, dense net, inception. Almost the models nowadays will have this kind of application where directly people can use it and directly they can work on it instead of writing a code from scratch, just like the way we have written above. Are you guys getting my point before we will proceed ahead to the last topic, that how it is better than AlexNet? Just refer at your home. I'm sharing a link. Also, if you can just simply search on Google, you will be able to get it. Shall we move ahead to the next topic if everyone is comfortable till so far? So now we have seen the two interesting CNN based models, right? So can anyone let me know Uh, how, and first of all, which specific model you find better and why? Because now you know the architecture of both of these models, AlexNet as well as VGGNet. So, what do you think? Which specific model is the better one, and why? So, let's try to have one chart with us. I will just try to take it from the web. And let's try to go in depth towards, first of all, the comparison between what we have covered up yesterday versus what we have covered up today. Because now you know both of them, right? If you will be able to compare the total parameters count with the table that we have created yesterday versus today, you will see that the total parameter count in VGG is quite huge as comparable to AlexNet. The reason is uh, the count of the number of layers, which is quite huge in VGG16 as comparable to AlexNet. AlexNet comes as the very first architecture as comparable to VGG16. So it comes in 2012, here it is 2014. If you will see the convolutional layers, that is the main reason why parameters are high. In AlexNet, we just have 5. In VGG16, 13 and 16, depending upon which specific model we are using. After that, we have 3 further dense layers. That is why total count, why it is called VGG16 is the number of layers. 13 we have as the convolutional layers, and 3 we have the fully connected layers. Why it is called VGG19? In that case, 16 we have as the convolutional layers. When I'm saying convolutional, I'm including convolutional plus max pooling. And 3 we will be having as the fully connected layer. So if you will try to add them, you will be able to see the count as 16 and 19. Now, this is not something which is important over here. The important thing is, if you will be able to see the kernel size in the uh, AlexNet versus VGG model, the interesting thing is in kernel size of convolutional part, in the AlexNet, it gets varied again and again. There is no as such, I would say, standardization that we have. And that is why it is very difficult for people who are working in the industry to remember the size. And that is where, if you remember in the very first class, I told you that you will find the kernel size 3 cross 3 is quite frequently used. And that is where they have standardized this kernel size as 3 cross 3, which is very easy to remember. Then if you will talk about max pooling, they have used 3 cross 3, but in the VGG part, they have used 2 cross 2. In terms of activation function, they are both same. In terms of dropout, again, 2 times dropping out, 50%, both are same. Final classifier, soft max of 1000 classes, both are same. So in a nutshell, if we will be able to observe, the difference, major difference lies in the fact that the count of, I would say, convolutional layers that we will be having, the kernel sizes that we will be having, and the activation function that we will be having. Considering these aspects, we are observing over here that VG model will have the more layers. Can I say everyone? As comparable to AlexNet, VG 16 ho or 19 ho, it is having more layers as comparable to AlexNet. And actually, this only difference helps to understand that why VGG model is a better version as comparable to AlexNet. When we are saying that it is having more layers, so what it will do in a way internally? More layers, will it be helpful or will it be a bad thing? Computation wise, they make the task simpler by having a simple kernel sizes, not a bigger one, and having a simpler max pooling. So now these more layers are actually helpful to extract more complex and hierarchical features in a given image, which basically helps the overall model to do a or to generate a better performance in recognizing fine details in an image, which AlexNet won't be able to recognize. So if you want to go in a lot more detail to extract the features from the given image, this, because it contains too many layers, so each and every layer will contribute to detect the features. So VGG16 will do a better job as comparable to AlexNet, right? So that is the main reason why this specific architecture is quite easier to, I would say, understand and implement, and why it is better in terms of performance as well. Getting my point? Is this clear? Any doubt? Anyone? Now, in the upcoming session, we will talk about the concept of transfer learning, which is a very interesting concept. Today, I'll not start this concept because if I'll start right now, then it won't be a good start. We will not able to finish the topic and we just have to leave in between, right? But whatever things we have covered up till so far, is this clear to everyone? So today, basically, we have seen again the, I would say, advanced CNN architectures, which will help to do the image classification task. Now, try to do one thing at your end. This is your today's task. We have a model by the name of ResNet. So if you will be able to observe in the documentation itself, ResNet also have different versions. So initially when it came, it was ResNet 50. Then after that, you will be able to see ResNet 101 is there, ResNet 152 is there, ResNet 50V2 as the second version we have, then 101 V2 we have, 152 version 2 we have. Again, this is kind of a simpler architecture once again, just like the way we have covered up AlexNet and VNet. Very widely used in the industries. If you can see over here, they have also worked on ImageNet data classification task to classify 1,000 images using the softmax function. This is I would say, again, a simpler way to implement the ResNet code. And this is what actually nowadays people are practicing to do. The if you will click on the source button, you will be able to get the entire structure with which this complete architecture is built, just like the way we have done in our live implementation part. So what you supposed to do is you supposed to check the ResNet architecture research paper at your end. So you will try to You can find any of the research paper. It will be available in Papers with Code, ResearchGate. Read paper, view the PDF, and this is the complete architecture you will be able to see, containing multiple layers, convolutional as well as max pooling, everything is there over here. So what you have to do is you need to get an understanding of the ResNet architecture at your end. In the next class, I will discuss what things you have observed in the ResNet architecture, how many number of convolutional layers we have, how basically it will work, how it will be able to determine the final output dimension size via that formula of n minus f plus 2p divided by s plus 1. And then how they are trying to work, because that is again a very bigger architecture. So how basically we can implement the same architecture via this specific parameters that we have in the keras.applications.resnet. So try to explore on your own. In the upcoming session, we will discuss about this specific architecture, as well as we'll talk about optimizers, as well as if time permits, we'll talk about transfer learning concepts. So we'll start with the transfer learning, and then step by step, we'll see how much we can cover up within that duration. So I hope the agenda is pretty much clear to everyone. So this is your today's task to explore and do some research on your own, so that whenever we will discuss this topic, it will be very easy for you to get the understanding, and we will not spend more time now further onwards to discuss about the architectures part, because initially I have taken it very slow, because it was the very initial architectures which we were discussing. Now from next architecture onwards, I won't spend this much time. Even I will check that whether it is required to implement the code from scratch for every architecture, because now I think you get the gist that how basically we have to implement it from scratch versus how the industries are following. So in upcoming sessions, we will try to write a code in the form of an industry standard fashion rather than writing it from scratch. So that's the whole point. But at the very end, at your end, you have to always check the code from scratch as well whenever you are doing or whenever you are learning for the very first time. Okay? Because live sessions have a limit. We cannot expand it beyond that. So you always have to learn it from your end. Self-learning is something which is required apart from attending these live classes. Then only you will be able to gain a better knowledge at the end of the day.